relativity. Lorentz had arrived at the formulae called the Lorentz transformation, which embody the whole mathematical essence of the special theory of relativity. But it was Einstein who showed that the whole thing was what we ought to have expected, and not a set of makeshift devices to account for surprising experimental results. Let's review the reasons which have made it necessary to substitute space-time for space and time. The old separation of space and time rested upon the belief that there was no ambiguity in saying that two events in distant places happened at the same time. Consequently, it was thought that we could describe the topography of the universe at a given instant in purely spatial terms. But now that simultaneity has become relative to a particular observer, this is no longer possible. What is, for one observer, a description of the state of the world at a given instant, is, for another observer, a series of events at various different times, whose relations are not merely spatial, but also temporal. We are concerned with events rather than with bodies. In the old theory, it was possible to consider a number of bodies all at the same instant, and since the time was the same for all of them, it could be ignored. But now we cannot do that if we are to obtain an objective account of physical occurrences. We must mention the time at which a body is to be considered, and thus we arrive at an event. When we know the time and place of an event in one observer's system of reckoning, we can calculate its time and place according to another observer. But we must know the time as well as the place, because we can no longer ask what is its place for the new observer at the same time as the old observer. There is no such thing as the same time for different observers unless they are at rest relative to each other. We need 4 measurements to fix a position, and 4 measurements fix the position of an event in space-time, not merely of a body in space. 3 measurements are not enough to fix any position. That is the essence of what is meant by the substitution of space-time for space and time. The special theory of relativity arose as a way of accounting for the facts of electromagnetism. We have here a somewhat curious history. In the 18th and early 19th centuries, the theory of electricity was wholly dominated by the Newtonian analogy. 2 electric charges attract each other if they are of different kinds, one positive and one negative, but repel each other if they are of the same kind. In each case, the force varies as the inverse square of the distance, as in the case of gravitation. This force was conceived as an action at a distance, until Faraday, by a number of remarkable experiments, demonstrated the effect of the intervening medium. Faraday was no mathematician. Clerk Maxwell first gave a mathematical form to the results suggested by Faraday's experiments. Moreover, Clerk Maxwell gave grounds for thinking that light is an electromagnetic phenomenon, consisting of electromagnetic waves. The medium for the transmission of electromagnetic effects could therefore be taken to be the ether, which had long been assumed for the transmission of light. The correctness of Maxwell's theory of light was proved by the experiments of Hertz in manufacturing electromagnetic waves. These experiments afford the basis for radio and radar. So far, we have a record of triumphant progress in which theory and experiment alternately assume the leading role. At the time of Hertz's experiments, the ether seemed securely established, and in just as strong a position as any other scientific hypothesis not capable of direct verification. But a new set of facts began to be discovered, and gradually the whole picture was changed. The movement which culminated with Hertz was a movement for making everything continuous. The ether was continuous, the waves in it were continuous, and it was hoped that matter would be found to consist of some continuous structure in the ether. But then came the discovery of the atomic structure of matter, and of the discrete structure of the atoms themselves. Atoms were believed to be built up of electrons, protons, and neutrons. The electron is a small particle bearing a definite charge of negative electricity. The proton bears a definite charge of positive electricity, while the neutron is not charged. It is only a matter of custom that the charge on the electron is called negative and the charge on the proton positive, rather than the other way round. It appeared probable that electricity was not to be found except in the form of the charges on the electron and proton. All electrons have exactly the same negative charge, and all protons have an exactly equal and opposite positive charge. Later on, other subatomic particles were discovered. Most of them are called mesons, or hyperons. All protons have exactly the same weight. They are about 1,800 times as heavy as electrons. All neutrons also have exactly the same weight. They are slightly heavier than protons. Mesons, of which there are several different kinds, weigh more than electrons but less than protons, while hyperons are heavier than protons or neutrons. These discoveries about the discrete structure of matter are inseparable from the discoveries of other so-called quantum phenomena, like the bright lines in the spectrum of an atom. It seems that all natural processes show a fundamental discontinuity whenever they can be measured with sufficient precision. Physics has thus had to digest new facts and face new problems. Although the quantum theory has existed in more or less its present form for 60 years, and the special theory of relativity for nearly a century, little progress was made until about 30 years ago in connecting the two together. Recent developments in the quantum theory have made it more consistent with special relativity, and these improvements have helped our understanding of the subatomic particles a good deal, but many serious difficulties remain. The problems solved by the special theory of relativity in its own right, quite apart from the quantum theory, are typified by the Michelson-Morley experiment. Assuming the correctness of Maxwell's theory of electromagnetism, there should have been certain discoverable effects of motion through the ether. In fact, there was none. Then there was the observed fact that a body in very rapid motion appears to increase its mass. Facts of this sort gradually accumulated, until it became imperative to find some theory which would account for them all. Maxwell's theory reduced itself to certain equations. Through all the revolutions which physics has undergone in the last century, these equations have remained standing. Indeed, they have continually grown in importance as well as in certainty. Maxwell's arguments in their favor were so shaky that the correctness of his results must almost be ascribed to intuition. Now, these equations were, of course, founded upon experiments in terrestrial laboratories. But there was a tacit assumption that the motion of the Earth through the ether could be ignored. In certain cases, such as the Michelson-Morley experiment, this ought not to have been possible without measurable error, but it turned out to be always possible. Physicists were faced with the odd difficulty that Maxwell's equations were more accurate than they should be. A very similar difficulty was explained by Galileo at the very beginning of modern physics. Most people think that if you let a weight drop, it will fall vertically. But if you try the experiment in the cabin of a moving ship, the weight falls in relation to the cabin, just as if the ship were at rest. For instance, if it starts from the middle of the ceiling, it will drop onto the middle of the floor. That is to say, from the point of view of an observer on the shore, it does not fall vertically, since it shares the motion of the ship. So long as the ship's motion is steady,